This is question 3 of the Regression Models textbook chapter on residuals, variance, and diagnostics. It refers to question 2 and 1 and says to perform an analysis of diagnostic measures including DF fits, DF betas, influence, and hat diagonals. So in the previous questions we've gone over fitting the data, and we've done that already, but let's do it again right there. So we fit the data that includes kilometers, petrol price, and the law, being a 0-1 variable, whether the seatbelt law had been enacted at that time. So a quick way to get the residual plots, to get some residual plots, is simply to do plot of the object that you assign the output to your fit. You have to hit return to see the next plot, and let me bring it into the recording window here. So the first plot shows residuals versus the fitted values. Here you're looking for any kind of pattern, and in this case it doesn't look too bad. It labels some plots that appear on the extrema, and it also fits a smoother through the residuals. This is because it's often difficult to ascertain a pattern when you're just looking at the points by themselves, but when you fit a smoother through it, often you can see patterns that you wouldn't have seen otherwise. Let's see the next plot. The normal QQ plot is done to ascertain normality of the errors. In this case, what you're looking for is whether or not your points fall mostly on a line. And in this case, it gives you the reference line. And typically, when you look at these plots, these deviations, for example, down here in the tails, which means that the residuals are larger in the left tail than the theoretical quantiles from the normal distribution, and they're I guess I mean smaller, larger in absolute value, smaller as in more negative in the tail on this side, and they're a little bit larger in the tail than one would expect than the theoretical quantiles in this tail. However, when you look at these plots, remember there's variability in the estimate of the quantiles from the standardized residuals. If you simulate data, even from a normal distribution, it's going to deviate from this line somewhat. So you want to see if there's any gross departures, not so much evaluating minor departures. In this case, this doesn't seem too bad. An instructor of mine at one point described it as the thick pencil test. So he would take a thick pencil, lay his QQ plot on a piece of paper down, and if his thick pencil covered up all the points, he would say, yeah, that's normal enough for me. And I think in this case you could argue this would probably satisfy the thick pencil test. Now let's look, there's some more plots. So the next one is the square root of the absolute value of the standardized residuals by the fitted values. This is the scale location plot. A smoother is put through it. And again, you're looking for patterns in this plot. It doesn't look so bad to me. And then the final one plots the residuals versus the leverage. Again, in this case, leverage, remember, is ascertaining how much potential for influence a point has by virtue of being outside of the norm for the collection of points. We might, for example, look at these couple of points that have fairly high leverage relative to all their other partners, and just see if there's anything out of the ordinary in those points. The R automatically labels some points potentially of interest, in this case ones that have high standardized residual values, but again these don't have terribly high leverage. Let's look at some influence measures as well. Just to remember though, maybe keep an eye out for the 12th and the 192nd point. So remember, we can look, for example, at the DF fits with the function DF fit. That isn't terribly useful because it just lists out a collection of numbers. But you can very easily just plot and look at the numbers. with plot, and then it plots it by the index. So now, when you look at it, on the vertical axis we see the DF fits, and on the horizontal axis we see just the index, the label index of the numbers. And so we might be looking for this, for example, 12th point and 192nd point that I was mentioning before, but this does not appear, to me this doesn't look like anything terribly out of the ordinary. There is maybe this point over here that has a little bit higher influence than most of the others. Maybe you might look at that point as well. Okay, let's look at the DF betas. So DF betas you can get with DF betas of the model, and I'm just going to print out a few rows. There's the DF betas. So notice we get a DF beta for every data point, but also for every coefficient. So let's look, I'm not too interested in the DF betas for the intercept, so let's just plot, for example, the one for the kilometers. And so I'm going to grab the second column of my DF betas and I'm going to plot it. And there we go. So in this case, we see some that are a little bit out of the ordinary that maybe are worth checking into here closer to the beginning. All right. Let's also maybe look at the DF betas for the petrol price. So what are we looking at when we look at this? We are looking at those points who the change in the coefficient for petrol price, whether or not this point was removed or included in the model. And in this case, some of these are maybe a little bit larger than the natural variation we're seeing in the DF betas. So then again, what you would want to do is you would want to go maybe look at some of these points and see about the whether or not there was a data recording error or there's something obviously wrong with that data point. Okay, so you could also look at Cook's distance. We can do that really quickly. Cook's distance is just Cook's distance of fit, and then you see it gives a list of numbers. Cook's distance is a summary over all points, so I'm just going to plot it again, which to me helps me look at it so that it's hard for me to look at a bunch of numbers. It's more easy to look at a plot. So Cook's distance is bounded from below by 0. It's a Mahalanobis distance, so it's a sort of guaranteed to be larger than 0. And again, for this, you're looking at any of them that are sort of well outside of the pattern. So this one seems to be very large, so we might want to look into that point as well. So again, Cook's distance is a weighted distance between the coefficients that we get if we included that point to the coefficients that we got if we excluded that point. So this point has a fairly large distance between whether or not we included it. Again, that doesn't necessarily mean we want to remove this point from our analysis or that this point is an outlier. It merely means that it's a little bit outside of the natural variation of the Cook's distance that we're seeing in the other points, and so why don't we just take a look at it. Okay, so then after you do these diagnostics and influence diagnostics, you usually want to print out the specific rows that you kind of got an interest in and look into them, particularly seeing if there was some sort of recording error.